Hi, I'm Luis,
I'm Andrea.
I'm Tyson.
and we're the UPA Floc blanket sub-team.
Our team was created to measure the performance of the Agua Clara Floc blanket to improve the sedimentation. This is a very important process because the water in the water treatment plants it's the main method for removing the suspended and coagulated particles in the drinking water. The flocs are clumps of particles that are created in the flocculator, and sedimentation occurs when these particles are removed through settling, which is the process by which the particles settle to the bottom of a liquid. And during this, a floc blanket, which is a layer of suspended particles, is created, and it captures particles that are too small to settle. The figure we have here is the tube settler we are using in our current apparatus, and is where sedimentation takes place, and it has a similar design to the one in Agua Clara treatment plant. The vertical portion is where the floc blanket forms and accumulates. The tilted portion on the top acts like the plate settlers in the Agua Clara plant and stops the particles from leaving the tank. And then we have finally the floc weir, which is identical to the one in the plant, that removes the excess of particles to maintain the floc blanket as a constant height. And to study this, we are going to focus on the floc blanket's stability, and we are going to use PID control. Our main goal is to find the optimal depth for the floc blanket to capture the most impurities and also reduce the frequency it has to be cleaned by workers. Once we have found the optimal depth, the Agua Clara will have a set height to put into the plants.
So what we're going to talk about next is previous work done by other floc blanket teams in the summer and also last year. So previous work on the floc blanket team involved changing the bottom geometry of the tube settler, and the changes in the bottom geometry of the tube settler allowed for the floc blanket to be active for a longer amount of time, because what happens is over time gelling occurs at the bottom of the tube settler, and what that gelling does is it prevents the upflow velocity from going into the tube settler, and it actually increases our effluent turbidity over time. And so by changing the bottom geometry of the tube settler, we were able to postpone how soon that gelling occurred. So the plan was to put sloped walls on the inside of the bottom geometry, and what the sloped walls do is they allow the flocs, when they fall on them, to fall into the upflow velocity and be resuspended in the tube settler. So that way gelling doesn't occur at the bottom of the tube settler. And so the importance of this really was just to reduce time in cleanup, because in an actual water treatment plant, you wouldn't really have this problem of flocs building up and like stopping your inflow velocity for the sedimentation tank. So this is purely just something to improve our lab cleanup time and give us more time for experimenting.
So this video demonstrates how our bottom geometry influences like the floc's recirculation and also resuspension into a tube settler. As you can see, the flocks are cycling up due to the upflow velocity. Previous work that was done in this using the high rate sedimentation sub-team previous semesters, they got these results. As you can see, the figure on the left, it shows minimal gelling because all the flocs are being resuspended up due to the upflow velocity. And the figure on the right demonstrates a linear increase in effluent turbidity. That's what we want. We do not want an exponential decay of the floc blanket or an exponential increase in effluent turbidity, because we want a stable floc blanket, and a stable floc blanket is only realized through a linear increase in effluent turbidity. Oh. So this semester we ran into troubles, a few troubles. First of all, we got leaks in our tube settlers when we were trying to recreate them. But then we consulted with the CEE workshop leader person. His name was Tim, and we plugged up those leaks. And also, we couldn't use previous semester's Procoda methods file because we had new pumps that wouldn't allow for those old codes to run. So that was our main struggle this semester. We had to work around that, and that really influenced how many experiments we ran. So our apparatus consisted of a water pump, waste pump, coagulant pump, clay pump, and also a coagulant tank, clay stock tank, and 2 turbidimeters, one for influent and one for effluent, a flocculator, and also a tube settler. The concentration of the packle was determined through Python code, which you can see in our report. Okay, so after consultation with our research advisors and Agua Clara's advisor, we determined these values for PID, which controls how much clay is pumped into our system. P was determined to have a value of 2.25 m's. I was determined to have a value of 640 m's, and D has a value of 0.
So as we said in the beginning, our team's original goal was to increase and change the height of the floc blanket and see how that affected our tube settler. And so our hypothesis for that goal was that an increase in the floc blanket height would lead to a more efficient sedimentation process. But we also sort of believe that there may be this optimal size that makes it like perfect for capturing the right amount of impurities in water. So we began running some trial experiments, and our first experiment was just a baseline experiment using the standard floc blanket height. We started this experiment off with a 10-minute warm-up state with just water. And so what that warm-up state does is it allows for us to clean out our tube settler and all the tubing and everything, just to make sure that when we run the experiment, everything's sort of in like a steady state. And so we just run this warm-up state in the beginning of every experiment. For our first experiment, we did not have PID control. And we were using a 40 RPM clay pump with a 1 millimeter per second upflow velocity. And so for our results for our baseline experiment, we did see air bubbles in the apparatus, which is not supposed to happen. We weren't sure exactly why we found air bubbles in the apparatus, but we looked into that, and we believe that that's why you see 2 spikes on the graph of the data between 10 and about 12 hours of running. And also the turbidity decreased after approximately 23 hours, which isn't normally characteristic of typical floc blanket behavior, because normally toward the end of the process, so it'll settle out at first, but then toward the end, you'll see an exponential increase on our graph of turbidity versus time. But we didn't see that this time, so we think air bubbles may have been the cause of that. We also saw that during our experiment, our turbidity values were out of the range that they normally are. So typically we want the turbidity to be between 0 and 10 NTU, but for this experiment, at first we had it around 95 NTU, and then later on it dropped to 30 NTU, but these are still outside the range of what we wanted for our experiment. So that was something we also analyzed and need to look into.
We also ran another baseline experiment, but this time using PID with the values that were mentioned previously. Again, our floc blanket didn't stabilize, as can be seen by the image. Here's an enlarged version of it. It didn't stabilize to our target NTU, which our target NTU for effluent turbidity, we want it to be a value less than 10, and this can be seen from this graph. It's only stabilized after the 32nd hour at like 125 NTU. That's not what we want, but it did stabilize. That's a good sign. And also, we need to fix our PDI values to so that influent turbidity can be at a desirable rate. That desirable rate is 100 NTUs. The image on the left represents our effluent turbidity, the one that we got and you saw in the previous slides, while the figure on the right represents the influent turbidity. As you can see, it's going everywhere. It's not stabilizing. So that's what we need to fix in our future work.
And now, as Tyson has just mentioned, the air bubbles have continued to be a problem, and regardless the use of the bottom geometry that previous teams have developed, and that has meant the decrease in the efficiency of the Floc blanket and the sedimentation tanks. And the future work of the team will be first of all fixing the PID values, and then once they are found, start experimenting with the different Floc blanket depths to find the optimal one and to implement it into the Agua Clara plants.